Thank you for being my backup in case I did forget that, but it seems like I managed to remember. So far, we only have a few of you here. Not yet, everyone. Let me go ahead and mark off the roll just to make sure I don't forget that. I know more people will coming, I'm sure, hopefully. Yep. I got y'all. So I asked before, but does anybody have any questions about past material, the test coming up, which obviously you're going to have during your lab on Thursday. So make sure you're prepared for that face to face, that sort of thing. That will cover for you guys. That should just cover chapters 19 and 20. And remember, 20's been cut down quite a bit. So coefficient of performance questions, quick and easy, fill in the right spots in the formula for the coefficient of performance. That's a fair problem. Uh, Calculate the Carnot efficiency of any heat engine, as well as calculate the efficiency of any heat engine. Again, those are just supposed to be straightforward types of problems. And then know your laws of thermodynamics and everything because it's potentially comprehensive. So you'll need to know exactly which one is Newton's first law, Newton's second law, and Newton's third law, Kepler's first law, Kepler's second law, Kepler's third law. Under what conditions is linear momentum conserved? And under what conditions is angular momentum conserved? And then zeroth law of thermodynamics, the first law of thermodynamics, second law of thermodynamics, and the third law of thermodynamics. Those are the major issues, but make sure you have those all prepared just in case. Again, I wouldn't necessarily demand that you have it memorized, but you should know it well enough where you can pick it out of a lineup of other phrases that might seem coherent and physically reasonable. So, no questions? All right, I was hoping I could hem and haw a little bit, get a few more minutes in. When we last talked, we had actually came up. You guys helped me with a derivation for a vector formula for the electric field due to a itty bitty piece of charge dq. So we imagined a vector r dq that points to the little bit of charge that actually causes a little bit of electric field. So that vector was called r sub dq. And then there was a r sub p vector that pointed from the origin to the point at which we wish to know the electric field strength. And we called that r sub p. We found that r sub p minus r sub dq is actually forms a line along which the electric field vector has to point. Now, if the dq is a positive charge, then the rp minus rdq gives exactly the right answer. If the dq is a negative charge, then that dq being there multiplied by the rp minus rdq, since it's negative, is going to flip the direction, and that makes it perfect as well. So the formula ended up becoming de is equal to dq times parenthesis rp minus rdq, close parenthesis, divided by 4 pi epsilon naught times parenthesis r what was it rp minus rdq close parenthesis cubed. So that's this I should say absolute value bars or magnitude bars or something like that as opposed to parentheses. But the fact that it was cubed, remember, came because we were trying to make that top vector into a unit vector. We needed the power of 2 in the bottom, but to make that whole vector on top become a unit vector, we had to divide it by a third one. So that became the third power. So hopefully everybody recalls that. We then worked a very specific problem, which I've told you there's various versions of it on my YouTube channel, so you can watch it over and over again. If you didn't follow that particular derivation, you can check out other ones. Like I said, there's probably 3 or 4 on my YouTube channel. But basically, it was an infinite distribution of charges all along the z-axis is the way I set it up, and it goes from negative infinity all the way up to positive infinity, and then somewhere around quote unquote the middle, was where the origin was, and then out along either the y-axis or the x-axis. I think I ended up doing it along the x-axis. But the main thing is I went a distance r away from the origin along the x-axis and computed the electric field there. We found out that basically only the X component or Y component, depending on whichever horizontal axis you were using, if you called it X or Y, basically that component was the only one that survived, and any Z components of the electric field actually cancel one another out due to symmetry. I showed you that that was true by symmetry, physically talking about, one little distribution of charge up here versus another one down here, and how this one's going to cause a Z component that points down, whereas this one's going to cause a Z component that points up. And for every one like that, you have another one just like the other one. So that symmetry predicts that we're not going to have any Z components. We did that. Then we actually computed it, set up the whole integral, got to that point, and I've managed to show you that that particular portion of the integral that had the Z component in it, that particular portion had a integrand that was odd. And when you integrate over a symmetric range with an odd function, then you automatically get zero. So I showed mathematically, again, a reason for it to be zero. And then finally, I just computed it as if we didn't know any of that, and that showed it was zero again. Okay, so we actually did 3 different ways of showing that. Now, that is about the second hardest problem that you could do in general in this physics course. The rest are quite easy compared to that one and the other one that you're going to learn when we first start doing sort of the equivalent of Coulomb's law, but magnetism. So when we do that, that's going to be the hardest of the hard that you could possibly do. So you might think, well, is this something I should be able to do? Yes, it's something that pops up as a single question on a face-to-face test. And usually I'll have it sort of cloaked in some way where it's a multiple choice problem. And of course, you've got to get the multiple choice part right. But then the multiple choice part might only count as 2 points, whereas the whole problem might count as 15 points. And you then have to take a photograph, or if you're face to face, which we will be because we're in lab, then you're actually going to submit a handwritten copy of you solving that problem with the problem number on the top of it and all that good stuff. So you actually turn in showing me your work so I can make sure that you actually can derive the right result. So yes, the infinite line charge along the z-axis is really not an unreasonable question to ask you, even on a final exam or a midterm or a single face-to-face test. What I would tell you to do to prep for that is, one, close your book and close your notes and close the video after watching it and feeling like you might have some sense of what to do, and then try to do it. And then you're going to run into a part where you forget what to do next, or you don't know what to do. And then you close what you're writing, look back at the video or look back at your notes, figure out how to do it, read the thing in its entirety, close your notes again, and then ideally I'd like you to start back over and see if you can start from the beginning again and go on. And keep doing that until you can get it done. Now, once that is done, you can then, challenge yourself a little bit by, let's say, not letting the extension of charge go all the way to negative infinity and all the way to positive infinity. You can do something simple like, what if it went only from negative L to positive L, and L was like some number way greater than R. That would be a way you could do it. And you can put numbers in there too. You don't have to just use Q's and lambdas and L's and that sort of stuff. You can actually make numbers for them and then integrate it from, R might be a specific answer you want for 1 meter. Then you could say, okay, let's do it from negative 10 meters to positive 10 meters. And then after you master that with numbers and or symbols, you might even try another version, which is, let's say you have that same wire of charge, but let's say the top is only 1 meter and the bottom is like 20 meters. Okay, so it goes up 1 meter and then it goes down 20 meters. So its whole length is 21 meters, and you're asking for the electric field at basically 1 meter down from the top, and then r distance over. So that's all cool. What is the title of this derivation? Okay, it should be. I'll actually look at the titles right now, and let me read them to you. Well, actually, I can actually do this too. I forget this technology is so nice. I can actually use share screen and show you the actual screen I'm looking at. All right. So yeah, this derivation I'm talking about, we did it yesterday, so it's definitely on, or I say yesterday, on the 13th we did it. And I just noticed, by the way, that our 13th video is not posted, so I don't know what happened, but I'll post that tonight as well. I'm looking back here and I'm looking for infinite line charge. That's normally what I use. In fact, let me do this. Let's type in infinite. Infinite well, particle and infinite well, infinite line of charge. So here's one of them. This is E field of infinite line of charge, infinite line of charge, Flux and Gauss's law, infinite plane of charge. That's one we're going to do in a few minutes. And infinite line, there's another one. So you can see I have way more than I even thought. But yeah, if you do the word, look for the word infinite or infinite space line, then you'll find probably every version of it. Okay, so let me stop that share. So yes, as I was saying, it would be good to make sure you can regurgitate that. And to be honest with you, I'm saying regurgitate, and I know that's a funny word to use, but it's literally basically what's going on. A lot of times when you're solving physics problems or learning physics problems for the first couple times, you're just acting like a trained monkey where you're doing A, B, and C, specifically because your teacher said do A, B, and C. Okay. And you don't necessarily understand it. And that doesn't mean that you're, not competent to do physics or you're not smart enough to do it. It just means that's the learning process most of us go through. We have hopefully some idea what's going on, but sometimes I literally have no idea what's going on. So that's happened with me, and I'm sure it's going to happen with you. So yeah, some of it's just rote memorization where you just spill your guts and do exactly what Mr. Younger said. However, after doing that 3 or 4 times, you're going to start to understand it. And then you can start, like I said, after you can get it yourself with symbols and even with numbers to make it a little easier. Sometimes do the numbers first and then the symbols. But then you can start considering cases where it doesn't go all the way to infinity. It only goes, to L and then to negative L, or where it's not symmetric. So it only goes up, a distance L above the origin, but a distance of 10L below the origin, that kind of thing. Those are all special things. And there's an extra credit problem that I normally will point out to you. I was just looking for it when I was waiting for class to start, but I haven't found it yet. So I don't want to write it up again. It was quite detailed to write it up. If I can find it, I will. But if you're interested in that, that's going to be another extra credit that'll help you. And we're going to see some more today. Okay. So anybody have any questions about that? Because I'm getting ready to take off from exactly the one we finished last time. And actually, I'm going to check and see exactly what that was, just to make sure I'm remembering correctly, because there is some probability that I don't remember exactly what we did last time. Ah, yes. I had did the infinite line charge, and I had broke it up into an integral called I sub x, an integral called I sub z. And yeah, I came back and I actually showed that the integral IZ was 0. Okay. So yeah, that was the last one we did. And the good news is I don't have to pull that result and then go to the next one, but that result is worthwhile looking at. So I will pull that up again anyways. So let me go ahead and share my screen. This time I'm going to share my screen with you regarding my iPad. That's a stream of words regarding my iPad. But anyways, I was just saying I'm using my iPad now, not the screen. There you go. So this is the last problem we solved. And notice, yes, that integral that you see actually goes from negative infinity to positive infinity. You see that the purple wire is essentially oriented along the z-axis, excuse me, and you see the arrow up by the Z with the 8 laying on its side, that means it goes to positive infinity, and the other one means it goes to negative infinity. But anyways, that was the problem we did. I'm going to start now with a blank page. I'll probably go ahead and start at the beginning instead of the end. I just added some more pages because I ran out the other day when I was solving some problems. So what I'm going to do now is I'm going to go ahead and write the equation that we found was the vector form of the equation for the electric field in Coulomb's law. So this is Coulomb's law for a continuous distribution of charges, one of which would be dq, and at a position rp vector. So what we were able to derive and use last time was basically that dE, that's a very small or very low magnitude electric field strength, is equal to, now what we're going to have here is a dQ. That's the differential charge element that's producing the electric field. That is in fact going to be on top of 4 pi epsilon naught, and then we're going to take the magnitude of the vector rp minus the vector r dq, take that magnitude, and I'm going to have to raise it to the third power, not the second power, but that's because one of them is doing the job of making a unit vector out of the vector that gives us the direction. And here's the vector that gives us direction. It's the p r sub p minus r sub dq. So that's the two vectors that you subtract, and that makes a vector parallel to the electric field. Unless q is negative, then the dq times that vector makes it the opposite direction. So it again points in the direction of the electric field. So it's a really ideal scenario. So that's what we're using. And what I want to do is do another use of that for a different configuration. I will point out to you that this right here is a vector from the origin. Remember, your coordinate systems that you make are completely up to you. So when I say it's a vector from the origin, it means wherever you chose your origin to be, and then it's going to be out to the position P that you want the electric field, again, in your coordinate system. So this is the vector from the origin to the point P at which you wish to know E. Okay, so that vector points from the origin to the point at which you wish to know the electric field. The dq points to the little bit of charge causing the electric field. Okay, again from the origin. So let me now draw a coordinate system again. Actually, I'll start off by drawing the charge distribution that I plan on analyzing. So what I'm going to do is imagine a loop of charge like this. So it's like a line charge, but it's looped around on itself. So it's like a bicycle inner tube or something like that. That's what we're shooting for. Okay. Oops, I got to turn on the chat and the participants. Okay, got all that. Got all this. Okay. Ooh. Okay, so this is supposed to be two, or basically just one like sort of inner tube shaped thing. My axis, in fact, is going to have the origin right at the center of this inner tube, and that's going to be my y-axis, and this is going to be my x-axis, and that's going to be my z-axis. And what I'm going to imagine is the point at which I wish to know the electric field is going to be the point P, which is right there. Okay. What I'm also going to say is that the radius from the origin to the inside edge of this inner tube shape is going to be capital R, and the thickness is going to be negligible. So in other words, the distance from the inside edge of the inner tube to the outside edge of the inner tube is essentially zero. So it's like a one-dimensional loop or ring or something. Okay. Now, with that in mind, I'm going to say it's uniformly distributed. So we have uh, given, oops, the loop shown below is a string of charge uniformly distributed and fashioned into a circle of radius, oops, r, and total charge. Oh, I just started writing in regular script instead of cursive. I don't know why. Okay, so there's the problem. So our formula we have listed above, so we know that's what we're going to start with. So I'm just going to write solution. And remember the other thing I gave you about this is we have dq such that it's either going to be lambda dl, and if the charge distribution is what we call uniformly distributed along a length L, then that lambda is a constant. Okay. However, if it's not along a one-dimensional string, for instance, it's over a two-dimensional surface, then it's sigma dA. And again, if this is uniformly distributed, the sigma is understood to be a constant. And finally, if it's over a volume, it's rho dV, and the rho would be considered a constant if it's uniformly distributed. But by saying that, I'm wanting you to realize that the lambda could actually be a function of x, or the sigma could be a function of x and y, or r and theta, or something like that. And the rho could be a function of x, y, and z, all sorts of stuff. So that's just the nature of it. And that's what we're going to use over and over again. What I'm going to do now is I'm going to go ahead and try to fill out the parts of this formula. This formula we have here, the DE formula, has specific parts, and the way we go about solving such a physics problem is just compute the individual parts. Now that we know it, put them all together, and then just start computing. So our solution, as I said, involves the formula above. So what I got to find is I got to find dq, I got to find rp, I got to find rdq, and that's pretty much it. We can run from there, because once I have those, then I can do RP minus RDQ and the magnitude of RP minus RDQ. So we'll start off with RP. RP is the vector that points from the origin to the point at which we wish to know the electric field. Can anybody guess what that RP will be? Speak out if you wish, but you can also type it in chat. Might not be so easy to do, but in principle, you can. Anyone? Okay, the notice on the picture, it says the point is there on the z-axis. So can anybody tell me the length of the vector? The vector RP, by the way.
Is it just Z?
Yes, Z is the magnitude. That's absolutely correct. I bet you also know what direction it points. Anyone? Don't be shy. It's fun to be part of the problem.
Is it like in the direction of the K unit vector?
Exactly. So that's really the whole answer. So what we do is we write R subscript P is just Z K hat. Okay. Now, the RDQ is a little more complicated. So I'm going to work that out for you. And I'm going to use polar slash cylindrical coordinates, which you should be familiar with polar coordinates, but cylindrical is just do polar coordinates and then add a Z axis sticking out of it. Okay. So using that kind of thought process, what I can do is I can say, imagine a line coming from the origin and that's at specifically an angle theta, okay? And then we allow that line to shift by an additional amount d theta. So that little itty bitty angle that I'm drawing right now is supposed to be infinitesimally small, and it's the angle d theta. So I'm gonna call that d theta. And then that forces this chunk right here. That whole chunk is my dq. Okay. Now, that length of it, like that length is actually given by r d theta. And using dq equals lambda dl, we can see that that means dq is actually equal to lambda times r times d theta. Okay? And what we normally entail as the vector, let's say the vector r dq, would be this blue guy right here. So that vector right there is r dq. And just to make the record clear here, actually, I'm going to use a different color. I'm going to draw the vector rp on here as well. So this vector is oops. This vector is r sub p. Okay. Now, anybody want to take a guess what the x component of RDQ is? If you're not familiar with it or you're not seeing it right now, that's okay. It's not the easiest thing to picture. A lot of people can't picture in 3D like that. Uh, so don't, feel too bad. But if anybody can, it might give you a little boost of confidence and make you feel like you understand what's going on. Let me give you a little help in case y'all might be on the verge of figuring it out. That little vector RDQ, its length is capital R. We do know that. And there's actually exists a right triangle lying in the XY plane, the two legs of which would be the components of that R vector. So for instance, we could say, I'm going to use this little gray color here. We could say that little gray component right there and that little gray component right there, those are our two components of the R vector. And that's a right triangle. So this little angle right here is 90 degrees. Now that I've said that, could anybody possibly tell me what is the X component of RDQ?
Is it like R cosine theta?
Exactly. Good job. So r cosine theta I hat plus r sine theta j hat. Now, notice I happen to have used the first quadrant from, two-dimensional space. That's key when you go to do these things. If you're trying to derive, for instance, the formula for that little dq, the best place to do it is either on the x-axis. Well, actually, that's like a second and third best. On the x-axis or on the y-axis is the second and third best, whereas in the first quadrant is the best to try, mainly because you're trying to look for it in its most natural state, and you have to throw in negatives and stuff like that. If you're in other quadrants, so it's better to just assume that. All right, so we've got RP, we've got RDQ. Now I got to compute RP minus RDQ. So RP minus RDQ is going to be ZK hat minus R cosine theta I hat minus r sine theta j hat, like that. Okay. And you can actually see what that vector is by, let's see, I'll draw it with a red vector. That vector right there is RP minus RDQ. Okay. Now I do that not just to show you where it is, but also that hopefully that you realize what the magnitude of RP minus RDQ is. It looks kind of confusing when you look at the vector RP minus RDQ, but if we look at that figure, I contend that it actually gets quite simple. So let's say, what is the magnitude of RP minus RDQ? Anybody see the short version that I'm leaning towards? Okay, so notice the blue leg in the XY plane, and then notice the green leg along the Z axis. Those are perpendicular to each other. Now, can you guess maybe what the magnitude is? I don't mind taking these chunks of class specifically because, there you go. Yes. I don't mind taking these chunks of class because specifically I really need you guys to try to engage enough to answer. So I feel bad when I'm talking at you, and that's what I feel like. So I just want to make sure I'm asking you guys. It looks like someone's starting to figure it out. Yes, it's going to be the square root of r squared plus r dq squared. That's basically what we're saying. Now, with that, what you might be missing by seeing that answer, it's somewhat correct. But notice that your vector is going to be z squared, or your square root, or your Pythagorean theorem is going to give you that the answer is going to be the square root of z squared plus parentheses negative r cosine theta close parentheses squared plus parenthesis negative r sine theta close parenthesis squared. But because those last two terms have an r in it, the r's can be canceled or factored out, and then you'll have r squared times parentheses sine squared plus cosine squared, which is just 1. So you ultimately just get r squared plus z squared square root. Okay. And that's what I hoped you'd be able to see just by realizing what that vector was when I drew the RP minus RDQ. So I was really, drawing that somewhat to show you that this is in fact a right triangle, and that the length of the green one is z and the length of the blue one is r, so it should just be r squared plus z squared. Any questions on that? Okay, now I'm going to make another argument just like I did before, specifically an argument about symmetry. So remember, the RP minus RDQ was the vector we chose to give us the actual direction of the electric field. So the vector parallel to that red guy would be, let's say, this one right here. So we can think of this as my DE vector. Okay. Now, what I want you to understand is when I have DQ right where it's drawn, which is the left edge of that little black slither, then if I go back here, I get a black slither like this, and that's the symmetrically placed other DQ. Okay, it's diametrically opposed. In other words, on the opposite side of the diameter of the circle. And in fact, it's going to create an identical DE vector in length, but the direction will be 180 degrees away from it. So, do you think this vector DE, when I add it for the front DQ and for the back DQ, when I add the DE in those two terms, are any of the vector components going to cancel each other out? I know that's a whole lot of words. Hopefully, y'all were following me enough to understand. If you don't, it's not necessarily that you don't understand. It's just a lot of words. Anyway.
Could you repeat it a little slower?
Yes. So notice the darker colored DQ that's towards the front of the ring, and then the other one that's barely shaded in towards the back of the ring. Everybody sees that? Those are both supposed to be infinitesimal. So really they should be right in under the crotch of the R there in the back one, and right at the tail of the red vector and the head of the blue vector for the front one. So it's just that little sliver. That both of those will create a DE vector, and the only one I'm showing is the one for the front one. The one from the back one would be basically in the same sort of spot, like I would draw it up like this, and then it would point this way. But those two vectors would be essentially identical, but flipped around 180 degrees. Okay. So what I'm asking you is, do any of the components of the vector DE, do any of them cancel out from the one from the front, which is the black one, versus the one from the back, which is the blue one?
Do the X and Y components cancel out?
Yes. In fact, the Z component is the only one that survives, but exactly the X and Y components are going to cancel each other out. That's wonderful to see because that's applying a physical understanding of symmetry. Okay. And it's predicting about the X components, it's predicting about the Y components. And we did it for just two. And of course, when you're talking about a circle, every little spot in the circle has a diametrically opposed counter spot that's going to cause that. So we basically know that when we integrate all this stuff, the integral that comes from this part and from this part are going to give us zero. Okay. So that saves us a lot of work. But I'm still going to go as if we didn't know, and I'll show you sort of where it comes out. But now we can go ahead and write out what our actual E is going to be. So E is equal to the integral of dE, which I'm going to call one, oops, I'm running out of space already. That's okay. I'll just stop when I get there. 1 over 4 pi epsilon naught integral. Now my dq is lambda r d theta. So I'm going to say lambda r d theta. There's my dq. I'm going to write in my rp minus rdq, which is going to be z k hat minus r cosine theta I hat minus r, oops, minus a different r, sine theta j hat. That's my entire vector. So we see my B-rad coming around the corner. So we now see the whole vectors fit in there. And now I got to take the difference, the distance between them, which is the r squared plus z squared square root. I'm going to raise that to the third power. So I'm going to get r squared plus z squared raised to the 3/2 power. Okay. So let's look at the z component first. So I'm going to say E sub z is going to be, I'm going to go ahead and pull out everything that's a constant from the integral above. So I can see that the lambda, the r, the z are all constants. So I'm going to write lambda r z over 4 pi epsilon naught r squared plus z squared to the 3/2. Okay, so that's all the stuff that came from the z term uh, that was a constant. Now I have what's left is the integral of, we've already taken care of the lambda, we've already taken care of the r, we've already taken care of the z. We're not putting the k hat just because we're talking about a component here, so we don't need the k hat. But we do have an integral d theta, and everything else has been taken care of, and we're integrating it from theta equals 0 to 2 pi. Okay, so we really made quick work out of that particular part of the integral. And in fact, remember I said the total charge is Q. So the fact that the total charge is Q tells us that lambda is equal to Q over 2 pi r. So that's going to come in handy as well, because when I integrate d theta from 0 to 2 pi, I just get 2 pi. So what's going to happen is I'm now going to have lambda times 2 pi r times z over 4 pi epsilon naught r squared plus z squared to the 3/2. And this lambda times 2 pi r is just q. So that's really what we're shooting for. And in fact, we get q times z over 4 pi epsilon naught r squared plus z squared to the 3/2. Okay, so that's that one. Now, that's the k hat term. So really, that could be written E is equal to this times k hat, based on the argument I already made, which said the I hat term and the j hat term are going to become 0 over integration. But now I'm going to go ahead and further justify or verify that for you. I'm also fixing that r that turned out so badly. Okay, so we've got the r's in there. Now what I'm going to do is write out E sub x. And E sub x, I'm also going to pull all the stuff out in front that's a constant. So I've got a lambda r squared like that, and a 4 pi epsilon naught r squared plus z squared to the 3/2. All that's been pulled out in front. And now I'm going to integrate. In this case, I'm going to integrate cosine theta, or actually there's a negative I have to put out in front, but I'm going to integrate cosine theta d theta, and I'm going to integrate it from theta equals 0 to 2 pi. Now, cosine is what we call our archetypal even function, because if you graph y equals cosine x, you'll see that it basically looks like, darn it, it basically looks like this. Okay, and then the other side is the mirror image of it, so it looks like that. So for instance, this is 2 pi This is negative 2 pi, and so on and so forth. That's the classic picture of a odd function, or excuse me, of an even function. So I'm going to also write that even to help you remember it, especially since I flubbed the wrong word up there a second ago. So this is an even function. And in this case, the evenness doesn't matter too much, but I just wanted to tell you that in general, if you integrate an even function, say from -5 to +5 or -4,000 to +4,000, anything symmetric like that, it's always going to integrate to zero. In this case, it integrates to zero for a slightly different reason. Specifically, we're going from 0 to 2 pi. And what you can see is, yes, this area right here and this area right here are both positive, but they also both happen to be exactly half of this area down here. So the integral from 0 to 2 pi is in fact 0. So all of that was basically to show that this is equal to 0. And then we do E sub y. Again, pulling out the extraneous stuff, I get a negative lambda r squared. And these are just the constants. I said extraneous. I really shouldn't call it extraneous, but just the stuff that's not going to play any role in the integral. And thank goodness, because that would have been ugly having to integrate all that nasty stuff, which, by the way, is going to happen in a few. So in this case, instead of cosine, we end up getting sine theta d theta. And it's kind of goofy for me even to have mentioned that even function and odd function in retrospect, but I think it's because I was remembering what I did last time and I couldn't remember if I had showed it to you. So anyways, the evenness and oddness helps. Again, this is a integral from 0 to 2 pi. So the evenness and oddness is not really a point at all in this integral. But again, it's helpful to know that sine is an odd function. So I want to reiterate that even though it's not that relevant to this integral. And I'm going to also show you what it looks like, and therefore you'll have it in your brain sort of hopefully as the, archetype even function, or in this case, it'll be an archetype odd function. So this is going to be y equals the sine of x, and this is going to be an odd function. Okay, now the way it looks is it goes up, reaches a max, come back down, reaches a min, and then comes back up, and a length of 2 pi, and it does the same thing here. So this is negative 2 pi, and this is 2 pi. But again, what you can see is if you were to integrate, for instance, at a symmetric spot, let's say from here, and then let's say that looks about like the same as this. If I actually were to integrate, what I would get is all this negative area, which happens to look like, in principle, basically, wait a second. Oh, I did it wrong. That last red line I did. Let me fix that. Okay. Here it is right here. So here's my negative area, and here is my positive area. But because I integrated over a symmetric range from the negative red line to the red line on the positive side, you can see that the blue area is exactly the opposite or negative of the green area if I had drawn it perfectly. But the main thing is we now have seen for this particular integral, which has nothing to do with that evenness or oddness. Like I said, I'm just reminding you because it's something that comes in handy with a lot of these problems. But for this case, we were actually integrating from 0 to 2 pi, which sort of is the same story as the cosine, except in that case, we had to use this little part being the positive and this little part being the negative. That integral from here to here to here is 0 because the total area is 0. Any questions on that one? All right, so the actual answer then is just E is equal to, now what I'm going to take is I'm going to take this guy right here and steal it. And then we'll put it here, paste. Okay, now that's not very big, but I can make it a little bigger, like that. Okay, and that negative is not there. That was actually part of the equal sign I was trying to grab, I think. But anyways, what we're going to say is this is the actual electric field for that particular problem that we just solved. So along the symmetry axis, directly above the ring of charge, of total charge Q, radius capital R, and distance Z above it, you have an electric field that is given by QZ over 4 pi epsilon naught times R squared plus Z squared to the 3/2 power. Okay. The reason why I wanted to make sure we got that answer is because we're going to use that now to solve yet another problem. So anybody have any questions on this one before we go on? All right, now that is also a good time to notice, for instance, how this would behave in the case of Z being way, way greater than R. In principle, Z being way, way greater than R, ultimately, you'd see that it's basically acting like a point charge because you're going to have the Z completely overwhelming the R because Z is approaching infinity, or infinite number times Z would be another way of thinking about, or infinite number times R would be another way of thinking about Z. If that happened, then that under the parentheses, or in the parentheses part, the R squared is going to become minuscule compared to Z squared. So you end up getting Z squared to the 3/2, which would be Z to the 3 in the bottom and a Z in the top. That cancels, giving you just a Z squared at the bottom, and you get Q over 4 pi epsilon naught Z squared. Exactly the answer that you expect for a point charge. So that's really, again, one of the things we try to do in physics, especially when we can work the answers out in terms of symbols, is we try to see, does this make sense with respect to the problems we've already solved? And of course, knowing the electric field for a point charge is Q over 4 pi epsilon naught R squared tells us that this exactly gives that result. Okay. Now let's solve another problem. Anybody have any questions again on this one? I know you hadn't asked any, but I just wanted to give you another chance to ask if you had any. Okay. All right, so let's go ahead and get started. This new problem I'm going to do is very much like the last problem. In fact, it's very much like it, but the difference is I'm actually going to make it a disk instead of a ring. So now I'm going to take this and embed this in the coordinate system of my choosing, which is going to be this guy, and this guy. So there's my x-axis, there's my y-axis, there's my z-axis, and the point P is right there. Okay. Now, in this case, it would be kind of hard to integrate using our formula. In other words, the DE formula I just calculated, because you need a infinitesimal differential charge element, dq. And in order to do that, you have to have like either the x variable, x value not changing over it, or the y value not changing over it, or the r value not changing over it, or the theta value not changing over it. If you try not allowing the r from polar coordinates or the theta from polar coordinates to not vary very much, then when theta doesn't vary very much, you just get a little a wall at some angle. going right through it. So you basically get this little bit right there. That's not very helpful. That's not repeating itself in the structure, so we can't really use that. If I try to do R holding constant, then I get a ring like this, which strictly speaking, does not have a vector that points to RDQ, right? Because the RDQ would have to be all of that around there. So I technically can't use the concept of RDQ to find that. Uh, in fact, what you're ultimately leaning to when you try to do this is we've eliminated the ability to just have a R or theta not change by a little bit. Uh, if we try to do a X not changing by a little bit, but by a little bit, then we get something like this, which is not conducive and not easy to integrate. If we try to do it for the Y, then it'd be something like this, not changing very much. Again, that's not very conducive for the integral because you're gonna have a range up to a square root and all that crazy stuff. So ultimately, what we decide is we can actually use the fact that the electric field we got above is for a ring of charge. So we're going to go and actually picture a little ring of charge, only instead of it being a ring of radius big R, it's going to be a ring of radius little r. And we're going to imagine that ring changing its radius from r equals 0 to r equal big R. And this quantity, in fact, is going to be called dq. If I do that and I use the formula above, then I can say solution E equals the integral of dE, which equals the integral of z dq over 4 pi epsilon naught r squared plus z squared to the 3 halves k hat. Okay, so that in principle is what I could use, only, oops, remember I said the radius is little r, so I'm going to put in a little r there instead of a big R. The z is still the same, and there's also, because this dq is actually equal to sigma times dA, and I'm going to say the area is 2 pi r dr, like that. So now you've got the r in the dq as well as the r in the denominator of the integrand. Okay. Now, remember, this thing has a finite thickness of dr, this little ring does. That's why it's 2 pi r dr, because we're imagining that the length of, like if we cut that ring and laid it out flat, we're imagining that both sides of it would have a length of 2 pi r. And then its thickness would be dr, so the area would be a rectangle, a rectangular area, so its area would be 2 pi r times dr. In reality, it's not really a rectangle. It's actually uh, a straight line, then a diagonal, and a diagonal on the other end. And the near side, the top side, is only a length 2 pi r, whereas the bottom side is a length 2 pi r, or 2 pi parentheses r plus dr, close parentheses. So it's, the two angles are exactly the same and that sort of stuff. But it turns out if you actually try to do that, and I've got a proof of it if you need to see it on various videos on my YouTube channel, but it turns out that if you actually calculate exactly what that area is supposed to be, which is like a thin ribbon of radius r, uh, it turns out that any other terms that you left off are of order of dr squared or larger. So that's why it's okay to do it. All right, now that we have that extra little sidebar, I'm going to go ahead and compute E. So E, oops, I guess we were using green. So E is going to be given by this. Now, remember the actual wording of this is find E. Or let me say find E at P. So that's the actual question. Now, what we have here is Z is going to be a constant. So I'm going to go ahead and pull that out in front. I'm going to pull out the Z on top and the 4 pi epsilon naught on bottom. And now what I'm going to have is the integral. Now dq we said was going to be sigma times 2 pi r dr. And then what we're going to do is have all of that over r squared plus z squared to the 3/2 power, and then the k hat. Now I can pass that k hat back and forth through the integral, no problem. Turns out I hat, j hat, and k hat are the ones we can do that with. If we're switching to other coordinate systems, there's rules and ways you have to actually compute those. But generally what you do is you break the if you have like a r hat or a theta hat or a phi hat, you break it down in terms of I hats and j hats and k hats and then integrate it. All right, now that we have all that, we're ready to actually roll and do the calculation. What I'm going to do is I'm going to say let u equal r squared plus z squared so that du is equal to 2r dr, like that. Okay, so I can go ahead and take this e. Oops. I can go ahead and take this E. I'm re-equaling it just because I wanted to have it start over further over here. So now what I have is a Z and a sigma and a pi over a 4 pi epsilon naught. And then I have an integral. Notice I left the 2r dr over there. So now we actually have the two. Oops, I meant to leave the pi over there too. So let me fix that. Okay, so I pulled the Z, I pulled the sigma, but I left the 2. I didn't want to leave the pi. I did want to leave the 2, but not the pi. Because D is 2r. That's what I looked at. I looked at 2 pi r. Sorry about that, folks. I'm putting the pi back. We're getting the pi back together. Okay. So with this in mind, we got 2r dr. That's exactly our du. That's all that's left over there. So I'm going to write du over u to the 3/2, which is not that pretty of a way to write it. And in fact, I'm going to go ahead and write it one more time. So now I'm going to say sigma pi z over 4 pi epsilon naught integral of u to the negative 3/2 du. Now, I didn't change the limits of integration, but you know I'm going to integrate from r equals 0 to big R. But I haven't put in the R yet, so I can just do that after I resubstitute back everything in. So the integral of u to the negative 3/2 is u to the negative 1/2 divided by negative 1/2. So now I can say sigma pi z. Again, I forgot to erase or to cancel out the pi's, but that's okay. We'll do it on the next pass. So this pi cancels out with that pi. But anyways, now I have u, which is r squared plus z squared to the negative 1/2 power divided by negative 1/2. So the whole reason I did that was that now I can see exactly where this 1/2 is going and all that good stuff. The k hat I'll put right here, and this has got to be evaluated from r equals 0 to r equals big R. I can see that the 1/2 is going to actually turn the 4 in the bottom to 2, and I am going to get a negative sign, so I'm going to say negative sigma z over 2 epsilon naught, and then I'll evaluate it at capital R, so that becomes 1 over the square root R squared plus Z squared. And then minus, this time we got to let R go to 0, so it's going to be 1 over just the absolute value of Z. Now, that's not the most convenient thing, and I still left off the K, so let me put the K in there too. But that's not the most convenient way. For starters, it's got a negative in front of it. And also, it turns out I know exactly what I want, so I'm going to distribute that Z through there. And what I'm going to say is the electric field, the actual answer now, is sigma over 2 epsilon naught. I absorbed that negative, remember, and that's because I'm flipping the order of subtraction. And when Z is divided by the absolute value of Z, you just get 1. Minus, now I'm going to have Z hit this, so it'll be Z over the square root of R squared plus Z squared. Just like that. This closes off that. This is in the k-hat direction. And that is our electric field at P. Okay. Any questions on that one? Okay. So just like I did consider the case of Z being much, 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 much greater than R in the equation at the top of this page, and we found that it was consistent with that of a point charge. Well, it turns out this is also something that we can analyze. For instance, one thing we know is that the discontinuity of a electric field component perpendicular to a surface, it differs by sigma over epsilon naught in going from inside of a conductor to outside of a conductor, but it's sigma over 2 epsilon naught in going from one side of a conductor to the other side of a conductor. So that sigma over 2 epsilon naught is something that's very important. Another thing we can do is we can see that just by thinking, if I get really close, for instance, to the surface of the disk, then that would correspond to a Z much, 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 much smaller than R. So if we look at this in the limit as R becomes much, much, much greater than, or excuse me, yeah, much, much greater than Z. So in this case, we get E is equal to sigma over 2 epsilon naught times 1 minus. Now, what I'm going to do is multiply by 1 over Z, or excuse me, 1 over R in the top and bottom. So this one's going to become Z over R for the numerator. And then down here, the 1 over R is going to go inside. That's going to make a 1 plus Z over R inside squared, all of that under the square root, and all of this times K. Now, when you take the limit as R goes to infinity, which is the same thing, or which is the same thing as assuming R is much bigger than Z. In that case, what you see happens is you end up getting the Z over R is essentially going to 0, and in the bottom is essentially going to 0 as well. But in the top, it in principle goes slightly faster. But you can see that it basically becomes either 0 if you look really, really close enough, or you can think of it as the R gets bigger and bigger, this 1 on the bottom survives, and you just get 1 minus Z over R. But Z over R, and the limit as R approaches infinity, is just 0. So we get E is approximately equal to sigma over 2 epsilon naught K hat. And that is something that comes in handy. We're going to see that in a little bit. Anybody have any questions on that part? Okay, I'm trying to remember if there's something else I wanted to do. I actually did it on my notepad. Actually, I'll look in the book real quick and see if there was another one because I actually happen to have it open specifically for such a need. But I thought I did another one this variety, but I might not have. Let's see. I did that one. I did this one. Yes. Ah, okay. Yeah, so there is something else that I wanted to do. I just remember I just considered one example of R being much greater than Z, but we could actually do it a little more severely, and in that case, we get basically the same sort of result. So you could use, for instance, the binomial theorem that you'll see in the inside cover of your book, which I know most of you did not buy a physical copy of the book, but you'll recognize it from the stuff at the bottom of the practice test as well as the stuff at the bottom of the face-to-face test because I just took and made copies of the inside cover. For this one, we have an actual existence of an electric field. And if you get close enough to that disk of charge that's uniformly charged, that's the whole reason sigma is basically the unit of charge per unit area. So it's like coulombs per square meter. That sigma was a constant. That's what made it uniform. Okay. So when we have that sort of situation and we actually get really close to the Z, it's as almost, or really close to the plane, it's almost as if the thing's infinitely large. And if you do that binomial expansion, you'll get a formula that shows that as well. But anyways, let's go ahead to what's next. I've talked about how when you get really close to this disk, you can get a electric field that's approximately sigma over 2 epsilon naught. So let me show you another neat little trick. Uh, Starting with this one, here's another example. Ah, darn it. Whoa, that really looks bad. Okay, so here's another example. Let's imagine this. We have two really ginormous plates. They could be circular plates. I'm just drawing them rectangular here just because it's easier to draw rectangles and see that they're foreshortened because they're so big and that sort of stuff, whereas doing a circle like that's a little harder. But let's imagine that this little separation between them, this little d, is way, 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 way smaller than r, which remember that was for a circle, but we could say this diagonal is greater than r. Okay. So when you see that, you're saying, oh, okay, so I've been told now that I'm between two parallel plates, and those parallel plates are really big compared to me. So, in fact, the distance that the edge is from me might as well be infinitely far away. I'm closer to the other one than I am from the infinitely far away one. But what we're going to do is we're going to assume that this one on the left is a positively uniformly charged plate, and this one on the right is a negatively uniformly charged plate. Okay. So if we look between them, what we're going to see is this is straight on instead of the view that I had before. So if I look straight on like this, then what I'm going to see is this side is the positive and this side is the negative, and the electric field due to the positive one is going to point. So if I'm right here at this little dot, which way is the electric field due to the left one going to point? Can anybody tell me that answer? The answers are right or left or up or down or into the page or out of the page. So we're looking at basically this edge right here. That's what this is. Okay. this edge right here is this. Hopefully that'll help you. Can anybody tell me? No right hand rule yet. Not yet, anyways. So remember the Q that we used, which gave us the sigma. The Q is actually sigma, or excuse me, the sigma is actually Q divided by pi r squared, where r is the big R. That's what that sigma is. So if the charge is positive, then that sigma is going to be positive. And what we found was the electric field pointed away from the disk. So that should tell you that the electric field due to the positive plate will point to the right. If I want to compute the electric field due to the negative plate, call it E negative. In this case, I'm talking about the same point or, equivalent point. I think you all see that if that plate on the right is negatively charged, then a positive charge will want to go to the right. And that's the definition of what direction an electric field is. Electric field points in the direction in which a positive charge would move. So this has to go that way. So the reason why I'm saying that is notice the formula that we got when we're in such a situation as being close to the disk is that the electric field does not depend on anything but sigma and this permittivity of free space. So what we've just learned is that I've got a electric field from the positive plate that's going to be sigma over 2 epsilon naught, and it's going to point to the right. And then I got a sigma from the negative plate that's going to create an electric field, and that's also pointing to the right, and that's also sigma over 2 epsilon naught. So the electric field inside is equal to sigma over epsilon naught. And in this case, we might call that in the I hat direction, say, because it's going to the right. Okay, so we just discovered something neat. It turns out if you put these two plates next to each other and one's positive and one's negative, then they make the electric field even stronger between them. And if you do the same thing on the outside edges, what you'll see is the positive plate still points to the right, but the negative plate now points to the electric field due to it now points to the left. So E equals 0 outside. Similarly, if you do the same thing over here, in this case, the electric field due to the positive plate is pointing out, and the electric field due to the negative plate is pushing to the right. So again, we get E equals 0 outside. So we now know what the electric field is between two parallel plates, assuming that the distance they're separated by d is way less than the distance across the plate r. Okay. Any questions on that one? All right. Well, it's almost time. Well, actually, no, I'm going to go ahead and let's give you 7 minutes. So come back at 6:55. Come back at 6:55. I'm right here. If you have any questions, you can still ask them, but I just wanted to give you guys a break because I got a little bit more stuff I'm going to cover before I let you go. I should probably point out that this stuff's not on the test on Thursday, by the way. It only goes through chapter 20. Let's see. Hmm. All right. Covered up my own clock. I've got 2 minutes. I've got 2 more minutes if anybody has any questions still. All right, I guess we should go ahead and get started. Again, just want to ask anybody, does anybody have any questions on how any of that transpired, answering these problems where I calculated the electric field at a distance z above a circle of radius big R, and total charge, well, I could look at it as if it had a uniform charge. Sigma equals a constant. And in fact, sigma would equal the total charge divided by pi r squared. So we did that computation, and then I used that result to find out what happens if in the event that z is much, 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 much smaller than r, then it's almost like you're up against an infinite wall. And that happens, what you find is the electric field is a constant, and that constant is sigma over 2 epsilon naught k hat. Now, the physical part about this that I like is we just derived the formula yesterday or last time for an infinitely long straight line of charge. Okay. So imagine an infinitely long straight line of charge. And when we integrated that, we got a formula that was basically lambda over 2 pi epsilon naught times r. So the electric field strength felt like 1 over r, whereas for a point charge, the electric field strength falls like 1 over r squared. So we had a point particle that has no physical dimensions left, right, in, out, or up, down. The electric field felt like 1 over r squared. When we had an infinitely long but infinitely thin one-dimensional distribution of charge, that felt like 1 over r. And now we've got one that's basically infinitely large, left, right, and up, down. So two-dimensionally infinitely large. In that case, we found the electric field that didn't depend on the distance at all. It was just a constant. Now, that exactly mimics how you've seen lighting work. For instance, if you look in a older house, especially, like some really old single and 2 room and 3 room houses that you might find in some of the poorest of neighborhoods and stuff like that, or some of the older houses, what you'll find is a single light bulb hanging in the top of a center of a room. That single light bulb makes the whole room feel, yes, brighter when you're near it, but really quite dark and nasty. And the reason why is at, for instance, 1 foot away from the light bulb, you have an electric field which is related to the brightness of the light. But then at 2 feet away from that same light bulb, the brightness of the light is 4 times less because it goes like 1 over r squared. So it ends up looking very dark around the floor, very dark around all the walls, and just the center looks bright. That's what a light bulb does. So if you go to a lot of stores, they know that's kind of a depressing mood, and people don't want a low lit environment like that to buy, for instance, groceries and stuff. So what they found is they can use these incandescent lights, the fluorescent ones, and they use long tubes. Well, long tubes are nice because if they're really long compared to the distance from the floor to the ceiling, then hanging them on the ceiling means their light's only going to fall like 1 over r, just like the electric field did for the infinite line charge. So if you're, for instance, 1 foot away from the fluorescent light, you have a certain brightness. If you're 2 feet away, you're only half as bright. But if you're, if you'd done that with a light bulb and going from 1 foot away to 2 foot away, it dropped to 1/4 as bright. Here it only drops half, and if you go 3 times as far, it only drops to a third, so on and so forth. So that is a lot more filling light. Then, if you really go to some other stores, you'll see that they've taken the time to not only put in long lights like that, but then they put a diffusion plate on top of it. So that actually makes it look like the whole rectangle is lit. And that's basically a close attempt of trying to make an infinitely large plate, because the infinitely large plate would make it no brighter at the floor than it is at the ceiling, because the floor is just as close to zero as the ceiling is. Remember, when you're comparing left and right and saying that's infinity, then straight down is zero or very close to zero compared to infinity. All right. So that's some neat little sidebar stuff that can help you figure that out. One thing we have done, remember we studied, let me show you specifically. One of the first problems we worked was calculating the force due to 2 point charges that were a distance apart and equal but opposite. Notice Q1 and Q2 here were positive and negative 3 microcoulombs. So they're equal charges but opposite in sign. They were separated by some distance. I even called it an electric dipole, as you can see right here. Okay, so these two charges, which are positive and negative 3 × 10⁻⁶ microcoulombs, those two charges form what's called an electric dipole. So now what I'm going to do is show you a neat result that we can use for an electric dipole. And the cooler thing about it is when we start studying magnetism, there's something called a magnetic dipole, and you get exactly the same results. So you start to see how the electric field and magnetic field are sort of opposite sides of the same coin. So what I'm going to do is I'm going to imagine a scenario where we're going to have a bunch of electric field lines from left to right. So what I'm imagining here is the electric field strength is uniform throughout this area, and that it points from left to right. And now what I'm going to do is I'm going to put a dipole in it. So I'm going to start off by putting this little positive, or excuse me, this little negative charge there, and this little positive charge here. Okay. So what that means, remember I said the formula, as you see written here, the formula for P, which is the symbol we use for the electric dipole P, the formula is the charge Q, the magnitude of it, times D, the separation between them. And it's a vector quantity that points from the negative charge to the positive charge. Specifically, I said note that the P points in the opposite direction as the electric field caused by the two charges. Notice if you actually had an electric field, it would point from the positive charge to the negative, and this points exactly the opposite direction. So that'll help you keep that straight. But now that we have that, we can go ahead and draw our P vector, and our P vector is going to be this quantity. Oops. I'm going to try to move it over just a little bit. So that's the actual dipole moment vector. What I'm going to say about that is this angle right here is theta. Okay. Now, if we imagine this actual thing, what we see is the motion that is going to result from this dipole being in this electric field is this negative charge right here. Let me go ahead and mark the signs on it. There's the negative right there, and there's the positive over here. The positive charge goes the direction of the electric field, and the negative charge goes the opposite direction. So I think what you can see is this thing is going to tend to rotate like that. And rotation, of course, is covered by torque, and we know torque is supposed to be force times lever arm, but really you need to make sure the force that you use is the component of the force that's perpendicular to the lever arm, or use the whole force and then use the component of the lever arm that's perpendicular to the force. Either way works. They're really saying the same thing. So what I'm going to do is calculate that torque. So the torque on this dipole moment is, notice the distance d is the length of that vector. So the lever arm, if I imagine it rotating, for instance, right about here, the center, call that the pivot point. If I do that, then the torque is going to be 1/2 d, that's the lever arm. The force is going to be, remember the formula for force due to an electric field is Q times E. So the charge times the electric field is the force. But what we see is that force is actually going to be, let's use a different color. I want to say purple. That force is actually going to be exactly this way on this one. And oops, I did that backwards. Sorry about that. I was thinking I drew the positive one down here. And I did actually in my derivation when I was practicing, prepping for class. So this is the actual force on the negative charge, and this is the actual force on the positive charge. Okay, and it's Q times E. But the main thing is I need the component that's perpendicular to the lever arm. So I really need the component like this. So I'm going to say, let's do a blue vector. That's the F minus. All right, let's say that is the force on the negative particle that happens to be parallel to the electric field, or I should have said perpendicular to the lever arm. Okay. And similarly, this one would be, darn it, this one would be F positive perpendicular. Okay. Now, remember this angle right here that I showed you is actually theta. So that's the actual angle theta. If you notice, this angle would be 90 minus theta, and then this angle would be theta again. And that gives you that this angle right here would be theta. So if I want the actual component of F that's actually perpendicular to the lever arm, then I'm going to have to say times the sine of theta. So that's just due to that one's just due to the negative charge. Now the same thing works out for the positive charge. You're going to get 1/2 d times QE, which is the magnitude of the force. And then again, this exact same problem works out. You've got basically this angle right here is theta, and you have to use the sine theta on that one again, so you get sine theta. So what you realize is you can now add these two, and you end up getting Q times D times E times the sine of theta, which looks a lot like, since it has the two vectors, this vector right here, QD, is like the P vector, but just its magnitude. And this vector right here is like the E vector, but again, just its magnitude. So then we jump to the correct conclusion that torque is actually equal to P cross E. That's the derivation we were shooting for. And now we've worked it out. So I know the formula for torque on a dipole and electric field. Now, while we're at it, we can say U is the potential energy is equal to the work done. And in this case, we're going to say, remember, work is equal to the integral of f dx. But there was another version that we covered when we were talking about circular motion, and we could get basically torque times d theta. So if I choose to integrate that, what I can do is I can say the torque, which is P times E times the sine of theta, is going to be the integral of P times E times the sine of theta. The P and the E are constant, and the integral of sine is negative cosine, so we get negative cosine theta. Now that happens to look like two vectors with a cosine theta, and that, of course, is exactly the formula for a dot product. So what we also find is that the potential energy of a dipole in an electric field is given by negative P dot E. So that's some results we can make use of. Sometimes it requires you to actually create the vector. So remember, one way you can create a vector is you can take the point values like x comma y comma z for the head and subtract from that x comma y comma z from the tail, and you'd be, x head minus x tail is the x component of the vector, and then y head minus y tail is the y component, and z head minus z tail is the z component. And that's an easy way to just get a vector between 2 points in space. And then you can, of course, make that a unit vector by calculating the magnitude and dividing that through. And then if you wanted that vector to have units of charge times distance, then you just calculate the distance between the charges and multiply that by the charge of each charge, in other words, the magnitude of it, and multiply that by your unit vector. Now you have a p vector. Okay, so that's just, again, some vector algebra stuff that you sort of need to know on occasion. And I wanted to lay that out for you. You can always subtract final point, which is where the head of the vector is, minus the initial point, acting like the x's in the point are x components, the y's are y components, and the z's are z components. Anybody have any questions on that? Okay, so we've actually finished chapter 21 now. There's plenty of examples that I left you in the module. There's examples on my YouTube channel as well. But now I'm going on to chapter 22, which is where we're going to use something called Gauss's law. So chapter 22 is, I'm double checking the name because I don't like to write down the name of a chapter and then have it be something different. But I am correct. It is Gauss's law. Now, I usually write mine differently from other people. It looks like, nope, I wrote mine the same as Giancoli did. So this is Gauss's law. And Gauss's law involves something called flux. So there's a quantity, phi, and we sometimes have to say phi sub E because it turns out there's a electric flux and there's a magnetic flux and then there's political flux and all sorts of different words. But this is called the electric flux. Through an area, and I mean specifically an area. It can be like a little rectangular area. It can be a circular area. It can be a circular area that's not even flat. It could be, part of a circle transcribed or circumscribed on the actual surface of a sphere, and then it'd be all over that surface. But the main thing is it's an electric flux through an area, and it's sort of sort of a measure of how many E field lines pass through the area. Okay. So imagine this, for instance. Imagine we had uh like a sunroof or something like that, a big chunk of basically rectangular window. And we wanted to, in some sense, keep track of how much light's coming through. Well, I'm drawing it in 3 dimensions here, but if the light came in, say, at this angle, and this is the perpendicular to the surface, then this angle would be called the angle of incidence. Now, I think you'd all agree that if theta equals 0 degrees, then more light will pass through the window. Would y'all agree with that? Does that make sense? If it actually goes through the window perpendicular, then all of the light would go through. Whereas if it's got a little angle, some of it could be deflected by the side walls or whatever for when it actually goes into the glass, that sort of thing. So the holy grail of getting light to go through a window is have the window exactly perpendicular to the rays of light. Does that make sense to everyone? Because that's the crux of the definition of electric flux. So if you really want to think about electric flux, then you see electric flux is directly proportional to the electric field, because a stronger electric field means more light gets through. It's directly proportional to the area, which area in this case means the area of the shape. Okay. But also it's related to how close they are perpendicularly. So, in other words, if they're exactly perpendicular, it's a one-to-one thing. If they're exactly parallel, then it's something different. Okay. But what we do when we go to talk about areas is we imagine a rectangular area or circular area or whatever. We imagine it lying in the plane of the glass, and then we represent that area as dA as a vector. Okay. And that magnitude of that vector is actually just dA, and then it points in some direction normal to the surface. So I put dA in hat. So if you define the direction of A to be consistent with that of dA, then you'd see that E and A being parallel or anti-parallel would correspond to theta equals 0. And that's the best case scenario. So what we're looking for is something where if A and E are parallel, then we get 1 or maybe even -1. Whereas if A and E are different than 0, or different than parallel, then whatever angle they are should dampen the amount of flux that goes through. So does anybody know of any trig functions, for instance, that for 0 degrees would come out to be 1, or for maybe 90 degrees would come out to be 1, or excuse me, 180, not 90, but 0 and 180, one has to be 1, the other one has to be -1. And then 90 degrees would be the worst case scenario. So we'd want it to be 0. Anybody know of a trig function like that?
Cosine.
Yep. So that's it. And in fact, what we ultimately do define the electric flux to be, it's equal to the integral of E, the electric field vector field, dotted with a infinitesimal area vector dA, defined like it was on that picture. This is the definition of flux. Okay, so you can do simple little things like they'll give you the electric field strength and they'll draw a little drawing and you can see the electric field vectors are like 30 degrees from the normal to the window. So then you'd say, oh, okay, well the angle's 30 degrees, so I'm going to take the magnitude of E, multiply it by the area, and then multiply that by cosine of 30 degrees. That's the typical examples you do. Uh, Really trivial, not much need for me to show you those examples. They're in the book, they're easy. What I want to do is jump right into Gauss's law, where we're going to use that expression, that electric flux. But in order for it to be about Gauss's law, it can only be the flux through a closed surface. So we're going to imagine a surface that has a clear inside and outside. So for instance, a toilet paper roll, just thinking of the things that my dog's bringing to me. So, so with a toilet paper roll, that looks like it has an inside and an outside, but notice, unless it's got caps on the end, I can go from back here inside the tube. I can come out here like that, and now I'm outside and I never cross through a wall. So a paper towel or toilet paper tube is not a closed surface. But if you had a paper towel or a toilet paper tube that was one that had actual end caps, okay, then what you'd have is this is being a surface, this is being a surface like that. And then if I actually tried to take something out of it, I'd have to literally bust a hole in it and then have it come out. So this is a closed surface. So Gauss's law is something that only applies when we're dealing with closed surfaces, something that has a clear inside or outside. And the way they make sure you remember that is they tell you to calculate the closed integral of E dot dA. Okay, so that's what I'm going to try to figure out what that quantity is, and hopefully you'll follow me doing it. And in so doing, you'll have a deeper understanding of exactly what Gauss's law is and why it says what it does. So what I'm going to do is I'm going to take a certain example case, a case that we could make in an everyday environment, and use what we already know about the electric field and calculate the flux coming through a closed surface. And I'm going to choose a very, very smart closed surface. Okay. Not because it only works with very specific closed surfaces, but because it's really hard to do math on anything but the simplest of surfaces. So let's go for it. So the question I'm answering is, what is the closed integral of E dot dA? Okay, so what I'm going to do is I'm going to draw a coordinate system. You know, I really shouldn't draw the coordinate system first, but I'm going to anyways. Okay, pull that out real quick. This is going to be my x-axis. This is going to be my y-axis. This is going to be my z-axis. And now what I'm going to do is I'm going to put a point charge. This is going to be a charge Q. At the origin. Okay. Now, I need to calculate E dot dA. That's what that formula up there says. It's a dot product with the electric field. Remember, an electric field or any field in general is an assignment to every point in space a specific value. In the case of the electric field, it's a vector quantity in units of newtons per Coulomb, and every point x comma y comma z in some particular part of space has been assigned a electric field in both magnitude and direction at that point. So what I need to do is then take that electric field and dot it with a differential area element dA that is perpendicular to the surface everywhere on the surface. So in order for me to do that and pull off that integral, it would be really, really helpful if the electric field E happened to be exactly parallel to the dA vector, because then E dot dA is just EdA. I don't even need the cosine there because it's automatically like that, right? And not only that, it turns out that when you're actually parallel to the electric field, then any surface perpendicular to that is a equipotential surface, like we learned about in the electric fields lab. That equipotential surface means specifically that the electric field is going to be a constant on it. And therefore, you don't even have to compute the integral because the E is going to be a constant and fall out in front of the integral, and you're just going to get the integral of dA. So that's what I'm looking for. That was a lot of words there, and I don't necessarily think you understood exactly what I was saying, but by all means, I definitely recommend you turn back to this portion of the video and listen to those words. I want a surface that is everywhere. The electric field on that surface will be perpendicular to that surface because it happens to be parallel to the dA vector at that particular point. So I'm looking for a surface on which the electric field would be a constant. Does anybody know, based on your understanding of the electric field from Coulomb's law, does anybody know what kind of surface would make an electric field that's constant on it? Let me write down Coulomb's law. So that's Coulomb's law for the electric field for a point charge at the origin, say, r being a distance away, and r hat being the vector that points from the origin to the point at which you wish to know the electric field. So can anybody now guess what kind of surface I need to make so that this integral can be done easily? All right. Well, I'll let y'all think about that a little bit. And while you're thinking about it, I'm going to try to uh, make a really good, clear circle. That's not an easy thing to do, but I'm going to try to do it. Okay. So let me try to draw a sphere, which looks like a circle in 2 dimensions, like that. Okay. Did it happen to have a center about where I wanted it to, so that worked out really well. In fact, the center goes something like this, or the sphere goes something like this, and then like that, and then back around like that, and then this part goes around like this. So I'm just trying to draw these so you have some understanding of exactly what this shape is in 3 dimensions. Now, I happen to know a really nice coordinate system that we can use, and specifically, actually, I should probably take those circles off because they turned out really bad, really badly. But anyways, ooh. But I've found a surface that works really well for us, and obviously that surface is a sphere. And it looks like this. Okay. Now, I happen to know a nice coordinate system to use in this as well, and it's spherical coordinates. So what I'm going to do is I'm going to say that this little quantity right here is a little rectangular window on the surface of the sphere. Okay. And it's not obvious what it is, but I will tell you exactly what it is. And then later when you guys learn about uh, spherical coordinates, you'll actually learn exactly why I said what it was. Okay. But basically, that's our little dA. That dA vector right there is a vector whose magnitude is exactly equal to the area of the little rectangle I drew, and its direction points radially outward here. I have the arrow tilted a little bit more than it should be. It should literally be leaning left a little bit more, but the main thing is I got that. So what I'm going to tell you dA is dA is going to be, it turns out that this vertical arc right here, that little arc and that little arc, that one is just related to r, the polar or the spherical coordinate r times d phi. Okay. Basically, the angle phi goes all the way down from 0 to pi. So what I'm going to say is this dA has a height that is actually equal to r times d phi, where again, phi is the angle down this way. Now, if you project this out onto the XY plane, then you'll see that this angle right here is theta, and therefore this horizontal part of the rectangle here and here, that is actually a length r times the sine of phi, because I need this component down here, which is the sine of phi times r. Okay. So for me to compute what this is, I'm going to now say sine of phi times r times d theta. And that d theta is that little change right there that I just drew in here. And it points radially outward. So I'm going to say it's the r hat vector, which you can derive on your own as well. I'm probably going to have to do that for my YouTube channel. I've done it for cylindrical coordinates. I just haven't done it for polar coordinates or for spherical coordinates. And that is the origin of those weird formulas that you use in dynamics if you had your dynamic series. Okay, so that's what our dA vector is. Now, I'll also tell you that since our charge in the center is Q, then this formula E equals 4 pi epsilon naught r squared times r hat, that is the actual electric field that we're going to use. So I can now compute that the flux is equal to the closed integral of E dot dA becomes the integral. Now, I've already established that this sphere is a closed circle, so I don't, a closed surface, so I don't need to put the closed symbol on there anymore. It doesn't make the calculus any different. It's just a circle in the integral to remind you that it's supposed to be done over a surface that has a clear inside and outside, and a surface through which you have to penetrate one of the walls to go from inside to outside or vice versa. So in this case, it's going to be Q over 4 pi epsilon naught r squared. And since the Q is at the origin, the spherical coordinate r is exactly the distance away from the point P and the charge Q. Now that E has to be dotted with dA And our dA, if I rejigger this a little bit, notice I got r d phi, r sine phi, d theta. I'm going to put it in a little bit more reasonable order. I'm going to call this r squared. And then I'm going to say sine phi, d phi. And then I'm going to say d theta. And then r hat. And that's got to be dotted. Okay. Well, the dot product, like the cross product, are what we call linear operators. So when I say that, let's say A vector is equal to A times I hat, or AX times I hat, and let's say B, now let's just say A is equal to A times I hat, and let's say B is equal to uh, BX I hat plus BY J hat, like that. If I wish to calculate A dot B, then that's A I hat dotted with BX I hat plus BY J hat. So when I go distribute this, I get A I hat dotted with BX I hat, and then I get plus A I hat dotted with BY J hat. What linear means is I can write A and BX out in front and then just tackle I hat dot I hat like that. And of course, that also means I can do the same thing over here. I can say this is going to be A, BY, and then I hat dot J hat. So that's what linearity means. It means that you can pull those constants out in front. So for us, what that's going to tell us is I've got, and I don't have to leave all this in the integral. I just don't want to take too many steps at once. I'm going to say Q over 4 pi epsilon naught r squared. That's one of the constants out in front of the vector. And then I'm going to say that times r squared sine phi, and then I'm going to say d phi d theta, and then I'm going to write r hat dot r hat. And remember, A dot B is also equal to the magnitude of A times the magnitude of B times the cosine of the angle between them. So that means this is going to be 1 times the cosine of 0 degrees, which means this is just 1. Everybody follow that? I know you haven't done double integrals, so that d theta and that d phi both being in there might be a little scary. It's not that big a deal, though. And I'm not going to make you do this again or ever. Okay, I'm just showing it to you so we will establish exactly what Gauss's law tells us. So now I'm going to go with the next line. Now that we've computed all that, I can see, for instance, that this r squared down here is going to cancel out with that r squared up there. And I'm going to pull the stuff that's constant out in front. So I'm going to have a Q over 4 pi epsilon naught. That's all going in front. And then I'm going to have an integral of, now I'm grouping the terms together for the right integral. So for instance, the sine phi is going to go with the d phi, and that's going to make one integral. And then the other one's going to be d theta, and that's going to make another integral. So that's how I'm handling this quote unquote double integral, which y'all are not supposed to have seen before. But phi is going to be integrated from 0 to pi, and d theta is going to involve theta being integrated from 0 to 2 pi. Okay. So that's just the range of those variables in spherical coordinates. But now I'm going to continue on. I've got Q over 4 pi epsilon naught. And then the integral of sine phi d phi is negative cosine because the derivative of cosine is negative sine. So the derivative of negative cosine is positive sine. So I'm going to say negative of cosine phi, and that's going to have to be evaluated from 0 to pi. And then the integral of d phi is just, or excuse me, of d theta is just theta, and that's from 0 to 2 pi. So I get q over 4 pi epsilon naught. Now I'm going to put a negative in front of it, and then I'm going to take the cosine of pi and subtract from that the cosine of 0. And then, of course, I'm going to take 2 pi and subtract from it 0 as well. And I shouldn't have even put that in there because it makes it confusing, but we'll just say 0 radians. Okay. But you see that the cosine of pi is -1, and that's going to combine with the negative symbol to give me a positive. So ultimately, all I get is q over 4 pi epsilon naught times, in this case, it's, oh, and this is 1, -1 minus -1. This is +1, so -1 minus 1. So that gives me a 2 because I've already canceled out the negative sign with it. And then this gives me a 2 pi from the second integral. So ultimately, the result is just q over epsilon naught. And that's what I'm shooting for. In fact, Gauss's law is the closed integral of E dot dA is equal to Q enclosed over epsilon naught. So whatever Q you have enclosed, that's going to go on the right-hand side and be divided by epsilon 0, and you will automatically get the left-hand side being the flux. Now, we actually did define a very specific direction, but it's only a specific direction for dA if the surface is closed. So like when I did this guy, I could have said dA points up or I could have said dA points down, and both would be acceptable. And my answers for flux on that could be different by, a negative sign. And that's okay. It never turns out to be a problem. What does turn out to be a problem is that sign really matters if it's a closed surface. So in the event of a closed surface, we define the dA vector to point radially outward. In other words, point in radial is not necessarily the word I want to go with because that makes you think it can only be a circle, but it can be anything. It can be, a cube, for instance. But it basically, the dA vector should always point as if it originated inside of the box or container or surface or whatever and is progressing outward. That way, your electric field lines would emanate from a positive charge and pierce the surface going outward. So that's what we're shooting for here. Now we have Gauss's law. We've actually derived it. And what I'm going to tell you about it is we're going to find the highly symmetric cases in which that left-hand side can be solved for E. That's the trick that we're doing here is we're going to use Gauss's law, which is Gauss's law. It's not Gauss's helpful hint that sometimes works. It's Gauss's law. So it's always true, at least within the realm of non-quantum electrodynamics, wherever that's true. It's if it differs from the Maxwell version of this, which is Gauss's law, then it wouldn't be true there. But other than that, it's always true. But we're going to solve for the integram. We're trying to solve for the magnitude of the electric field in Gauss's law, which happens to be part of an integral, which also happens to be part of a dot product, which also happens to be part of a vector field. We're going to solve for that magnitude of the electric field in certain symmetry cases. That's when you can use Gauss's law to solve for the electric field as in certain symmetry situations. Gauss's law is always true, but the way we're using it's a weird thing. So let me show you, for instance, that nasty problem that we did in chapter 21. Remember the infinitely long string of charge? Let's solve that using Gauss's law. So example. Use Gauss's law. Oops. To compute the electric field a distance r away from, whoops, an infinitely long uniformly charged wire. Assume lambda equals a constant is known. So in other words, I'm saying you can treat r and lambda as constants, or excuse me, as values that we know, and we're supposed to derive the formula in terms of that. We've already done that. Remember, we did that last time, and specifically, we did it right here, and we got lambda over 2 pi epsilon naught r for that. Okay. So now we're going to do it with Gauss's law, and you're probably thinking, "Oh crap, his alarm went off. We're going to run out of time." But that's really how beautiful this is it's lightning fast. So I'm going to draw my coordinates real fast, and I'm going to say, here's the solution. So drawing my coordinates, I'm going to draw them just like I did before. So that's my z-axis. And that's my x-axis. And I am going to have a wire of charge right here and right here. It's supposed to be really, really thin. Goes on forever this way, goes on forever this way. And right here at a distance r away is the point P. Okay. So what I'm going to do, actually, let me put it in a little closer. You'll see why in a second. But anyways, I'm going to put the distance that it is away a little bit closer. That's going to be a distance r, and this is going to be the point P. Okay. So what I'm going to do is I'm going to choose a Gaussian surface such that the left-hand side, which is the closed integral of E dot dA, becomes just E times an area, and the right-hand side is Q enclosed. Okay? Over epsilon naught. So what I'm going to do is I'm going to draw a Gaussian surface, and here's my Gaussian surface. And here's my Gaussian surface. Whoops. Now, by choosing it this way, I've done something really smart because I know everywhere on this outside surface, the electric field is perpendicular to it. So the stuff works out really nice. And then up here on the top, this would be like my little differential area element, and my dA would equal some dA times k hat. My dA down here would be dA. I'm going to call that one dA top. This one dA bottom. This one's going to be negative dA k hat. And then over here, for instance, my dA would look like this, and it would point radially outward. And this is what I'm going to call dA. And I put SL on there because this looks like a soup can, and I'm talking about the soup label portion of the can. In this case, it's going to be dA times R hat, where R hat is the cylindrical coordinates, R hat, our polar coordinates. Okay, so now that I have that, oh crap, we're almost out of time. We only got a couple minutes left. So now I got to do the left-hand side. Left-hand side, Gauss's law. And this is the way you do it because you've got to work both sides simultaneously. So the left-hand side is the closed integral of E dot dA, which means you have to go over a whole integral surface. That's going to be the integral evaluated on the top of the integral of the E field evaluated on the top times dA for the top plus the integral of the E field evaluated on the bottom times dA for the bottom plus the integral of the electric field over the soup label dotted with the dA for the soup label. And I have to compute that now. So first off, the integral of the electric field on the top, what we're going to do is we're going to make the assumption that assume E is equal to, what I'm going to say is I expect it to depend on X and Y or R. So I'll just call it E of R, which is also the same thing as E of X and Y. Sort of. And I think it's going to point in the radial direction, R hat. Again, cylindrical radial direction. So that's my hypothesis. So when I put this in, I get, when I put this in, I get the integral of E of R hat, dotted with dA k hat. Now, R hat doesn't have a Z component. That's why I kept telling you that it's a cylindrical R hat. It doesn't have a K component at all. So the dot product is going to give you 0 on that one. And I'll show that in a second. Plus over here, I'm going to have E of R hat, dotted with negative dA k hat, because that's for the bottom. And that was for the top. And then I'm going to have plus integral E of R hat, dotted with dA R hat, like that. Now, what I get is the integral of E of R dA. I'm using the linearity of the dot product to write R hat dot K hat. But we know that R hat dot K hat is 1 times the cosine of 90 degrees. So that is 0. That's why it came out to be 0. We also have the same thing for the other side. It's going to be integral negative E of R dA R hat dot K hat, which again is 0. And then we have plus. Now, in this case, we're actually on the surface of a cylinder whose radius is R. So E of R is very much a constant. It comes out in front. And then we have the integral of dA times R hat dot R hat, but R hat dot R hat is 1 times the cosine of 0, which of course is just 1. Okay. So I get the integral of dA, which is just the integral of the surface area A, right? Oh, by the way, I should call this length right here I'm going to say that's L. That'll come in handy. But anyways, I now get that the uh, left-hand side is actually equal to E of R times A. The right-hand side, this is the part that potentially gets hard. All that stuff that I just did was me explaining all of it to you. You should probably, when you're doing a test, though, you're probably going to write this. You might write that just to show me that what you're talking about is right, and then you're going to write this. That's it. Like all this other stuff is me just showing you how it works. So you don't need to write all that. The right-hand side is Q enclosed over epsilon naught. And what we said was uh, the charge per unit length is lambda. So the charge enclosed must be lambda times L. Or you could say, for instance, Q is equal to the integral of dq, which equals the integral of lambda d z in this case, which equals lambda times L, because I'm going to go from negative L over 2 to L over 2. So that's the total charge that happens. So the charge enclosed is lambda times L, and I'll deal with that area in a second. So what the area turned out to be, by the way, is the area for the surface of a soup can label, which is another reason that I took the time to call it a soup label, is if you actually took and cut with a razor knife down the side of the soup label, laid it out, it would be a rectangle, and the height of that rectangle would be L, and the length of that rectangle would be 2 pi r. So the area is 2 pi r times L, and now I can set left-hand side equal right-hand side. We'll do more of these next time, but I'll finish this one up. I get E of R times 2 pi r L is equal to lambda L over epsilon naught. You can see that the L's actually cancel each other out, and you're ultimately left with E is equal to, remember our hypothesis was that E of R times R hat was what it is, and sure enough, we're getting lambda over 2 pi R, or excuse me, lambda over 2 pi epsilon naught R in the R hat direction, which for us, we could also call it the X hat direction. Okay, because it was along the X axis. But that's it. And that's exactly the same result we got when we did it last time. Lambda over 2 pi epsilon naught R in the I hat direction. And now we see lambda over 2 pi epsilon naught R in the R hat direction. Same thing here. So that's it. That's how we're going to use Gauss's law. Don't freak out too much. It is kind of weird. It will take a little while, but the left-hand side is always going to be electric field strength times an area. And a lot of times you're just going to use A for it. Sometimes you have to use 2 pi RL like I did here or some other thing. But the main thing is the hard stuff comes on the right. You guys are free to go. Thanks for coming. I'm sorry I kept you 5 minutes over. But you're free to go. And of course, you're always free to go if you have to leave right at time. The video is going to catch whatever you miss anyway. So y'all have a good one, guys. Good luck on your exam next time. Feel free to stick around and ask me questions. Send me text messages between then and now in case you have any other questions. I'll be glad to help you. Or you can contact Mr. Raskovic as well. Have a good one. Thank you for coming. Dang, that was quick. They left. They had enough of all that. Oh well.